Statsproblems.com was used to create this tutorial, which can help us calculate a chi-square hypothesis test for independence. Let's begin by selecting one of the 25 example problems. The question appears in the blue box. Determine if the distributions of two nominal scale variables are independent. Observed frequencies are shown below. For row 1 and column 1, OBS 11, the observed frequency is 24. For row 1 and column 2, OBS 12, the observed frequency is 6. For row 2 and column 1, OBS 21, the observed frequency is 36. For row 2 and column 2, OBS 22, the observed frequency is 24. Alpha is 0.05. What are the results of the chi-square test of independence? Let's step through the solution by clicking on the Next Step button. In step 1, we calculate the sums of row, column, and all observed frequencies. For row frequencies, the sum of row 1 is the frequency of row 1 column 1, OBS 11, plus the frequency of row 1 column 2, OBS 12. In this example, the sum of row 1 is 24 plus 6, which works out to 30. The sum of row 2 is the frequency of row 2 column 1, OBS 21, plus the frequency of row 2 column 2, OBS 22. In this example, the sum of row 2 is 36 plus 24, which works out to 60. For column frequencies, the sum of column 1 is the frequency of row 1 column 1, OBS 11, plus the frequency of row 2 column 1, OBS 21. In this example, the sum of column 1 is 24 plus 36, which works out to 60. The sum of column 2 is the frequency of row 1 column 2, OBS 12, plus the frequency of row 2 column 2, OBS 22. In this example, the sum of column 2 is 6 plus 24, which works out to 30. For total frequencies, n equals the sum of all row frequencies. In this example, n equals sum of row 1, 30, plus the sum of row 2, 60, which works out to 90. In step 2, we calculate the expected frequencies for each cell. The expected frequency of each cell is the sum of column frequencies for the cell column, times the sum of the row frequencies for the cell row divided by the total number of frequencies, n. The expected frequency of cell 11 is the sum of frequencies for row 1, times the sum of frequencies for column 1, divided by the total number of frequencies, n. In this example, the expected frequency of cell 11 is 30 times 60 divided by 90, which works out to 1800 divided by 90, which works out to 20. The expected frequency of cell 12 is the sum of frequencies for row 1, times the sum of frequencies for column 2, divided by the total number of frequencies, n. In this example, the expected frequency of cell 12 is 30 times 30 divided by 90, which works out to 900 divided by 90, which works out to 10. The expected frequency of cell 21 is the sum of frequencies for row 2, times the sum of frequencies for column 1, divided by the total number of frequencies, n. In this example, the expected frequency of cell 21 is 60 times 60 divided by 90, which works out to 3600 divided by 90, which works out to 40. The expected frequency of cell 22 is the sum of frequencies for row 2, times the sum of frequencies for column 2, divided by the total number of frequencies, n. In this example, the expected frequency of cell 22 is 60 times 30 divided by 90, which works out to 1800 divided by 90, which works out to 20. In step 3, we calculate the chi-square values for each cell, defined by the row, R, and column, C. The chi-square value for a cell RC is the observed frequency RC, minus the expected frequency RC, squared divided by the expected frequency RC. For cell 11, the chi-square value is the observed frequency 11 minus the expected frequency 11 squared, divided by the expected frequency 11. In this example, the chi-square value for cell 11 is 24 minus 20 squared divided by 20, which works out to 4 squared divided by 20, which works out to 16 divided by 20, which works out to 0.8. For cell 12, the chi-square value is the observed frequency 12 minus the expected frequency 12 squared, divided by the expected frequency 12. In this example, the chi-square value for cell 12 is 6 minus 10 squared divided by 10, which works out to minus 4 squared divided by 10, which works out to 16 divided by 10, which works out to 1.6. For cell 21, the chi-square value is the observed frequency 21 minus the expected frequency 21 squared, divided by the expected frequency 21. In this example, the chi-square value for cell 21 is 36 minus 40 squared divided by 40, which works out to minus 4 squared divided by 40, which works out to 16 divided by 40, which works out to 0.4. For cell 22, the chi-square value is the observed frequency 22 minus the expected frequency 22 squared, divided by the expected frequency 22. In this example, the chi-square value for cell 22 is 24 minus 20 squared divided by 20, which works out to 4 squared divided by 20, which works out to 16 divided by 20, which works out to 0.8. In step 4, we calculate the sum of the chi-square values for all cells. The sum of the chi-square values for all cells equals the chi-square for cell 11, plus the chi-square for cell 12, plus the chi-square for cell 21, plus the chi-square for cell 22. In this example, the sum of the chi-square values equals 0.8 plus 1.6 plus 0.4 plus 0.8, which works out to 3.6. In step 5, we find the critical chi-square value. We need degrees of freedom to look up the critical value for the hypothesis test. In a chi-square test for independence, the degrees of freedom is the product of the degrees of freedom for the row variable and the degrees of freedom for the column variable. The degrees of freedom for the row, df row, equals the number of rows, r, minus 1. In this examples, df row equals 2 minus 1, which works out to 1. The degrees of freedom for the column, df col, equals the number of columns, c, minus 1. In this example, df col equals 2 minus 1, which works out to 1. The degrees of freedom are df row times df col. In this example, degrees of freedom equals 1 times 1, which works out to 1. With alpha equals 0.05, we need to look up the critical value for df equals 1. Use interactive table 10 to find critical chi-square value. Using the alpha equals 0.05 table and df equals 1, we find the critical chi-square value of 3.841. We close this window to return to the analysis, which shows the critical value from table with df equals 1 is 3.841. In step 6, we test the hypothesis. The observed chi-square value of 3.6 is less than the critical chi-square value of 3.841, so we fail to reject the null hypothesis. In addition to the 25 example problems, we can work step by step through an unlimited number of new problems using the Generate button. The Edit Data button can help us create problems with customized input. Instructors can use this function to create problems with complete solutions to use on exams, in class, or for homework. For printed output, we can print the question. Or we can print the question with the complete solution. The free website has statistical analyses in all of the most common areas in statistics. Statsproblems.com also has a mobile version so you can access the site from anywhere. For help with statistical concepts, HelpMeWithStats.com is a free website that has more than 70 tutorials, as videos, or as self-paced slideshows. In addition, HelpMeWithStats.com gives you free access to a comprehensive stats textbook with more than 685 review questions. Thanks for watching. If you find these resources valuable, please share StatsProblems.com and HelpMeWithStats.com with your friends and instructors.